Hello everyone, Professor Dustin here, and this video is going to be a quick introduction to superpositions of waves and interference patterns. So essentially, this is the problem we want to tackle, is that, say we have two traveling waves, a wave there and a wave there, moving towards each other. What happens when they collide? Well, they don't collide because waves are not physical objects. They're displacements of whatever, electric field, water, whatever. But when they interact with each other, that's called a superposition. The waves are sort of adding together as they hit each other. So if you're going to sort of carefully study that, you can go into the sort of sine and cosine stuff about waves and sort of use the trig identities to actually write down a mathematical equation for what the combination of those two waves are. I'm going to take a simpler approach and just look at the interference patterns when you observe these waves, and then we're going to get a lot of information about how they interact by just looking at these interference patterns. So to start with, let's do the two most basic examples, right? So now let's say the waves are traveling together, so they're easy to manage instead of going in opposite directions. I'm going to see what happens when we add one wave to another wave of the exact same type. So one wave and another wave added in phase. So the maxes are lined up and the mins are lined up. Or I'm going to add a wave which is completely out of phase with the other wave, meaning that the max is lined up with the min here, min with the max, max with the min, and so on. So you can probably tell what's going to happen here. These waves are going to add, so the max is going to get twice as big and the min is going to get twice as small, and so excuse the drawing, but it's going to look something like this, right? Exactly the same, but twice as big in amplitude. Okay, so if that's what happened there, you could probably guess what's going to happen down here. This max is going to hit this min, they're going to add together and give you 0. This min is going to hit this max, and that's going to add together and give you 0, and that's 0. So nothing. So basically these waves are adding together, and these waves are not adding together. They are subtracting from each other because every max hits a min and it gets canceled out. This is the two basic kinds of superposition and two basic kinds of interference. Constructive interference is when the waves add together to get bigger, and destructive interference is when they subtract to get smaller. Now, you can get gradations in between these guys, right? Like if this is just a little bit offset instead of being offset by a full half period, you can get sort of in between these two. But those are the cases we're not going to sort of deal with. We're really only going to deal with constructive interference or destructive interference. Okay, so let's think about a situation in which we would actually get this destructive or constructive interference like in real life. So I'm going to use sound waves because those are like something we can imagine, like creating sound waves like with a speaker, with an instrument, or with my voice, or whatever else. So there are two speakers, and I'm going to turn on some sound. The sound is going to have exactly the same wavelength. That actually matters. So if the wavelengths are a little bit different, constructive and destructive interference gets kind of complicated because the waves won't exactly cancel because they'll have different frequencies, different wavelengths, right? So same wavelength wave. Let's first look at what happens if because I need to observe, I'm going to listen to this sound somewhere in space. And I'm going to have like a sound that I hear from this speaker and a sound that I hear from this speaker, right? Well, let's do the easy case first, which is right in the middle. So let's say I'm standing right here and I'm listening to the sound from those two speakers, and I want to know if the sound is going to like amplify or get canceled. Well, from the middle point, it's pretty obvious what's going to happen. Any sound, and I guess I'm going to try to draw this best I can, that starts from that speaker is going to travel and reach the point like that. But the same frequency sound that starts from this speaker will do the exact same thing. So I'm going to try to draw the exact same wave. So I tried to draw the exact same wave. I did the best I can. But anyway, the point is, since the distance from here to there and here to there is exactly the same, when you get there, you get constructive interference because the two waves have traveled the same distance. They're in phase when they reach that equidistant point. So here's the trick. What if I move a little bit in either direction away from the center point where I'm definitely constructively interfering? Well, if I go over here a little bit, I'm shortening the path this wave takes, and I'm lengthening the path that wave takes. So I'm sort of forcing myself to observe the wave a little bit earlier here and forcing myself to observe the wave a little bit later there. So you can see that as I move away, I might get to a place where the waves are actually out of sync, where I'd moved exactly enough for the two distances the waves travel to make them out of phase. Well, that's how this works, right? Is you stand at different places and you observe either amplifications or cancellations from each of those waves, from each of these speakers. So let's try to think about like what would have to happen for me to find a place to have destructive interference. So I'm not going to try to draw the waves again because it's going to get super confusing. I'm just going to draw the distance. So distance here, call that D1. Distance here, call that D2. So what happens, in order to get destructive interference, the two distances have to be out of phase by half a wavelength, right? So we go back to our other picture, and I'll quickly draw that, right? So destructive interference was basically this. And you can see what's happening there is that the shift is half of a wavelength. So see how I'm going from one maximum down to one minimum. I'm taking the maximum, I'm dragging it over to the minimum. That's half a wavelength. So since I'm moving that half a wavelength, what I want is the differences in the distance, so d1 minus d2, make it positive d2 minus d1. I want that to be half a wavelength. So if that condition is true, the difference in the distances, and there's a special word for this, which I'll tell you in a second, but if this difference is a wavelength, is half a wavelength, then you get destructive interference. The technical word for this thing is PLD. The path length difference, because that's basically because the difference in the distances is a mouthful, right? So path length difference just says the difference in the distances. So there's some path length difference between that distance, and if that's exactly lambda over 2, half a wavelength, you get destructive interference. Now, this is actually just one condition, because of course, like, if you kept going, you might get to another place where instead of being half a wavelength, you're like 3/2 of a wavelength out, or 5/2 of the wavelength out, or so on and so forth, right? So the actual condition for destructive interference is that the path length difference is n plus a half over, times lambda. So what's happening here is you can see that for every n, you get a condition of destructive interference. Up here, I picked n equals 0. That was the first possible place where we could get destructive interference. N equals 0, 1/2 lambda, you get that. N equals 1, you get 3/2 lambda, you get the next place where you have the waves completely out of sync. N equals 2, you get 5/2 lambda, the next place. So that's the condition for destructive interference. You look for the path length difference to be n plus a half lambda for some n. You can pick whichever n you like, or maybe the problem says which n to use. There's a similar condition for constructive interference, and you might be able to guess what it is. It's the path length difference. Instead of being n plus a half, it's n times lambda. So if your path lengths if n is exactly 0, that means that the two path lengths are exactly the same distance. That's the path length difference is 0. That's a condition for the first constructive case. N equals 1, if the path length differences are exactly lambda, that means that the two shifts, let me just draw that. So there's one wavelength. The next one is shifted by a whole wavelength, so that you start here. That's a whole wavelength shift, but now see, you're constructive again, right? You shifted it by 1 lambda, and now again your maxes are lined up, your bins are lined up, and so on. So that's the condition for constructive interference. For every n, you can get a place where you get constructive interference. It's like there, further down there, whatever. And then for every half wavelength, you get destructive interference. Okay, so that's introducing the topic of destructive interference and constructive interference. Now let's do a simple problem. So this is going to be two speakers in a line. So instead of a two-dimensional picture, which is what we did for the sort of discussion of the theory, this is just going to be two speakers in a straight line in a one-dimensional situation. So these two speakers are going to be emitting a sound with the same frequency, 200 hertz. I'm going to pick a point P, which is going to be a distance d2 away from the close one, and the two speakers are going to be separated by a distance d1. So the distance from this speaker to P is going to be d1 plus d2, and from here to P is just going to be d2. So I want to know, how do I pick D1 and D2, the two distances between the speakers and from the rightmost speaker to P, so that the sound interferes constructively at point P? Okay, constructive is the key descriptor there. So that means the condition I want is the PLD, the path length difference, to be equal to sum n times lambda. So that's the condition. Now to apply the condition to this case, I have to actually calculate what the PLD is for this case. Well, that's going to be really easy. That's the difference in the distance that the sound travels. We have to be a little bit careful to make sure it's positive, so I'm going to make the bigger distance the first distance. The bigger distance is the distance from this speaker to P, so that distance is D1 plus D2. And then I'm going to subtract out the distance of the second speaker, which is just right there. That's how long that sound travels, is just D2 minus D2 is equal to sum n times lambda. All right, so that's our condition. Notice this condition gets really simple really quickly because the two d's cancel, right? There's a d2 right there minus a d2 there. So our condition is actually d1 n times lambda. So notice now for every n that we pick, we get a condition by which we can make sure that the interference at p is constructive. And notice that we actually know what lambda is because we know what the frequency of sound is, and for any sound, we have the condition that the velocity of the sound is going to be frequency times lambda, and for air, we know that the velocity of sound is 340 meters per second or so. So that means we can calculate what the lambda is here. If we do v divided by f, you get about 1.7 meters. So the wavelength of sound at a frequency of 200, which is a fairly lowish, not a very low note, but a kind of a low note, is about 1.7 meters. So that tells us that we have a number of ways we can pick what the distance is. That's why I didn't say find the distance, right? The condition is that as long as d1 is some n times the lambda, where lambda is 1.7, we can be sure that the interference at p will be constructive. So that means that we can pick d1 to be 1.7 meters, right? That's n equals 1. We could also pick n equals 2, and that means it's going to be 3.4 meters, right? And then we can keep going, 5.1, right? 5.1 meters, and so on. So every multiple of 1.7 gets us a particular condition on P. And of course, here it's even easier to sort of see what's happening here. That's why I picked this example. The waves, I'll just draw right on top of this. So what we're saying is that D1 has to be a multiple of the wavelength. Let's draw the first one. That's going to be one wavelength. There's one wavelength. So that means that when this wavelength is going to continue and is going to hit at P, but when I turn this speaker on, it's going to be in phase with that one, right? Let me draw a second one. If D1 is 3.4, twice the wavelength, that means that this one does this. That's one wavelength. That's 2. And then at that point, it keeps going. And then when the second speaker turns on, it's exactly in phase with that wave. So they add when they get to P. So you see what's happening? As long as I keep the two speakers some multiple of the wavelength apart from each other, then when the second one turns on, they will add together and create constructive interference at point P. So that's visually what's happening here. I could have done destructive interference too and just done an n plus a half over here and we could have found the same condition. But here are the kind of problems that we're going to solve in one dimension typically, and having to do with something like simple finding of constructive or destructive interference. The next thing to do here would be to study something called the double slit experiment, which was an actual experiment done by Thomas Young in 1801 that actually proved that light was a wave. Because if you can set up an experiment by which you are looking at the interference patterns of something like light from light, then you have just demonstrated that light actually acts like a wave if you can find these interference patterns, and that's what the double slit experiment is. But that's a separate topic for a different day. So thanks very much for watching this video. I hope it's been helpful, and I will see you guys in class.